Hello one and all. We are discussing infinite limits and how they will link to vertical asymptotes. This is part 2 of our videos. As we said earlier, an infinite limit generally occurs in either of two scenarios. Case 1, which was discussed in the previous video, occurs when the function has a denominator whose value is approaching 0. Case 2, the function contains a logarithm whose argument is approaching 0 from the right to respect its domain. In this section, we're going to discuss the second of these two situations and describe what it means about the function's graph. Recall that all logarithmic functions of the type log in base a of x have an infinite behavior around x equals 0. More specifically, for bases where a is greater than 0, approaching 0 from the right will tend to make log in base a of x tend towards minus infinity. For bases a between 0 and 1, the limit as x approaches 0 from the right for log in base a of x will tend towards plus infinity. In the first case, logarithms are increasing and therefore start from minus infinity. For bases between 0 and 1, logarithms are decreasing and therefore start from plus infinity. Here are examples of these functions. You've noticed that in green, log in base 1/2 of x starts from plus infinity and decreases through 0.10. Here's a base whose a value is between 0 and 1. The two other graphs display a logarithm in base 10 as well as a logarithm in base e, both of each start from minus infinity before crossing 10 and resuming its increasing trend. Right, so here's our summary. So in general, for a's that are less than 1 and greater than 0, obviously, plus infinity would be the trend as x goes towards 0 from the right, and minus infinity for cases where a is greater than 1. Of course, you may not remember the graphs for logarithmic functions all the time, so a numerical approach can be used to get an intuitive idea of what the result of, for instance, the log in base 2 of x will produce as x approaches 0 from the right. So I've selected a set of values for x that are approaching 0, remaining to its right, and here are values that log of x in base 2 will produce. We will most frequently be using the natural logarithm. It suffices to remember that as x approaches 0 from the right, ln of x tends towards minus infinity. In short, the infinite behavior clearly occurs when the argument inside the logarithmic function is approaching 0 from the right. So here is our rule number 2. Occasionally, when we perform direct substitution, we will write ln of 0 plus to be equal to minus infinity. Although, admittedly, the notation is not totally appropriate. This is why I'm using quotations. So this will be an agreement between you and I, and hence the term our rule. Here are a few examples that we can examine together. So in this first example, we are applying a limit as x approaches 3 from the right to ln of x squared minus 9. In terms of domain, we're okay since x approaching 3 from the right guarantees that x squared minus 9 is a positive number. So we are applying a ln function to a positive number. That number, however, is becoming increasingly close to 0 as 3 squared minus 9 would be 0 itself. So according to our rule number 2, ln of 0 plus will tend towards minus infinity. As a second example, we are making x approach 2 from the left this time, and applying this limit to the function x times ln of 2 minus x. If we were to do direct substitution, the x acting as the coefficient of ln of 2 minus x is simply becoming 2 or heading towards 2. As for the inner function of the ln, 2 minus x is becoming closer to 0, but remains positive since we are subtracting by a number slightly less than 2 itself. So we have another ln of 0 plus form. 2 is a fixed positive number, and it is multiplying an expression that is becoming really big and negative, and therefore the outcome will be negative infinity.